It begins quietly. A faint tremor, a shifting of earth beneath heavy rain. Then, the ground tears open. Hillsides collapse. Villages are swallowed whole. Landslides. Nature's silent, indiscriminate destroyer. For centuries, predicting them was a guessing game, a tragic lottery of geology and weather. But what if we could see these disasters before they struck? What if an unseen intelligence was already scanning the planet, detecting the subtle shifts, warning us before the inevitable? This isn't science fiction. It's happening, powered by an architecture most people never see. Every second, an invisible armada of satellites orbits our planet. They are the eyes of Earth, constantly collecting. Radar pulses pierce clouds. Multispectral cameras capture hidden biological signatures. Altimeters map ocean depths. The volume is staggering. Petabytes upon petabytes of raw, unprocessed data are beamed down daily. This isn't just imagery. It's a torrent of measurements, observations, and telemetry, an endless digital chronicle of our world. Over decades, this archive has grown to an incomprehensible scale, holding critical information on everything from global ocean conditions to the precise topography of remote mountain ranges. Most people imagine that artificial intelligence simply learns from this raw data, that you just feed the machine the entire unfiltered deluge, and it magically discerns patterns. But that's where everyone is profoundly mistaken. Imagine trying to build a sophisticated engine from a mountain of raw ore. You can't just toss the unrefined rocks into a furnace and expect a crankshaft. The ore is full of impurities, mixed with other elements, and utterly useless in its raw state for precision engineering. The same holds true for Earth observation data. Without refinement, it's just noise. The real intelligence doesn't emerge from raw data. It's forged in an unseen architecture of data refineries. This is where petabytes are painstakingly transformed. First, calibration. Raw sensor readings are adjusted to account for atmospheric interference, instrument drift, and solar angles. Then, normalization. Data from different satellites, captured under varying conditions, must be made comparable. It's like ensuring every ingredient in a complex recipe is measured using the same standard units. But the critical step is often less visible: annotation and structuring. Identifying a landslide in a satellite image requires defining its boundaries, classifying its type, linking it to geological surveys, turning pixels into meaningful information. This meticulous, often manual, work ensures the AI learns from clean, consistent examples, not chaos. It's only after this extensive refinement that foundation models like Prithvi can begin their work. Trained on these vast, meticulously structured datasets, they learn to perceive Earth in an entirely new way. They don't just see pixels, they identify relationships, predict changes, and understand context across immense geographical scales. Think of it as developing a universal translator for Earth's diverse languages: land cover, ocean currents, atmospheric chemistry. This generalist intelligence then forms the bedrock, capable of adapting to countless specialized tasks, from detecting subtle changes in a forest canopy to mapping the precise boundaries of coastal erosion. But this transformative power comes with significant trade-offs. The scale of these data refineries and the subsequent training of foundation models is immense. It consumes vast amounts of computational power, demanding energy footprints comparable to small cities. Then there's the hidden risk of bias. If the historical data used for training disproportionately represents certain regions, climates, or socioeconomic conditions, the AI's intelligence will be skewed, potentially failing in critical areas or perpetuating inequalities. The transparency of this unseen architecture becomes paramount. Understanding how these models are built and what data they're trained on is crucial for trusting their outputs, especially when deployed in high-stakes environmental or disaster response scenarios. With this refined intelligence, the picture changes entirely. The same AI that helps map global ocean health, identifying areas vulnerable to warming or pollution, is now being deployed to mitigate the silent catastrophe we saw earlier. Instead of simply reacting to landslides, specialized AI models, built upon foundation models like Prithvi, can analyze high-resolution topographical data, soil moisture content, and precipitation forecasts. They detect subtle precursory movements, generate real-time susceptibility maps, and even predict potential landslide trajectories, giving communities vital hours or days of warning. This isn't just data analysis, it's proactive planetary guardianship. The unseen architecture refining petabytes into intelligence is a continuous, evolving endeavor. As new satellite constellations launch, as our understanding of Earth's complex systems deepens, so too must the sophistication of these data refineries. The future lies not just in collecting more data, but in building even more robust, transparent, and ethically sound pipelines. It's about empowering specialized AI to not only observe our planet, but to become a vital partner in its stewardship. The quiet work of transforming raw signals into profound insights will define our ability to face Earth's greatest challenges, making the unseen architecture the most critical foundation for our shared future.